Hi, I'm Henrik. I'm the author of the Futureverse and the Future package and frameworks, and we have a few contributors to it too, like the FUR package was done by Davis. But today I'm super excited. This is a prototype, a proof of concept, because I've been changing things in the Futureverse and testing how easy it is to add new features. So I'm going to present today a peer-to-peer parallelization methods in R through the Futureverse. So that allows you to share compute among friends in the room, across the world. I'm at the University of California. I'm faculty in epibiostat. I'm with the Cancer Center. I'm engineer in my head. I'm trying to be a scientist, but I use the word but more than and. And I like to do applied stuff and share it with everyone. I'm also super stoked that the use R is coming back now after the pandemic. It's been a really big struggle. Last year we were in Salzburg. It was a success, and I'm super excited here. So thanks for the local organizers here to set this up. So this is good times. So futures. So if you're here to hear about future because of investment strategies, go to another room. This is about parallelization, okay? Who has used futures or Futureverse in R here? Okay. Who of you knows about the concept futures, the theory? Okay. So for everyone here, I'm going to do a very quick crash course. So you understand that it's not magic happening under the hood. So let's consider a very simple R assignment. So here is, when R sees this expression, it looks at the right-hand side saying there's 1 plus 2, and R says, I'm going to evaluate that, calculate that. And then in the second step, I'm going to assign it to variable A. We know that. It's so obvious to us, but things are happening behind the scenes. If you would write this with futures, you can split these two steps up. It looks very convoluted, but stay with me. So you can wrap this 1 plus 2 inside a future, and it will, you give R that thing. I forgot my preps here. And you give a handle F to that future. And later you say, I want the value to this, okay? So the analogy here is that you have the 1 plus 2, okay? That's the expression. You wrap it up in a box. This is very fast. You put the lid on, and you pass it on to R, and R does something here, okay? Later, you go back to this future and ask for the value. That's taking off the lid. If it's done, you can take off the lid. If it's still running, it's locked, okay? So you take it off, and let's see, result is 3, okay? Wow, okay. So we can do this with more fancy expressions. We have a data object, the vector 1 to 10, and we have a function that takes the sum of this and is a very slow implementation, so it will take 1 minute to do this. With futures, you would write it like this. You split it up, you put that expression and object in the box, and then you look at the box later. A little bit magic. Okay, so why this complicated setup? And by the way, this is the concept of futures is now 50 years old, mid-70s. When I started this, it was only 40 years old. Okay, so let's say why you want to do it, because of parallelization. So let's take a little bit more complicated example here. We have two vectors, xa and xb, and we want to calculate the sum of both. So when R gets to this point, it will process for 1 minute and get stuck there. And then after a minute, it can start working on this. And we get eventually A and B, and we can work with those data. And total processing time is 2 minutes here. Okay. With the futures, we can do this. We have the data. the first future here now, we put that in. Let's see if I got this right. We have this is my trick to try to slow down my talk. But so here we have the expression and the data object. So a future can also contain data, and we know that these like processing things are expressions and functions and data. It's a very math thing. I put this in here. I put the lid on, and I send it off somewhere to R. And the thing is, this step is much faster than I am. That's basically like 0 seconds, okay? So we already here, we get to this next one without waiting. And I have prepared this. I'm not going to unfold it, but that expression and this data object is, I put it in here, closing the lid, putting it down. So now these are processing somehow, I don't know how, but R takes care of this. And if we run in a parallel setup, both of them are going to be processed at the same time. And so if we go and ask for the value after like 5 seconds, because now our main R prompt, you can do whatever, these happening in background. After 5 seconds, we go say ask for the value of the first. Now this lid is still locked. So it's going to be locked for 55 seconds. So it's finished after 1 minute. So I take it off, and there is the, oh, that was the second one. I opened the B first. Doesn't really matter, that's the B. Okay, so now I have that value. And then I open A. And since these two run in parallel, they both unlock the lids about the same time. So I now got the other future. So now I hold both A and B here. And then I can continue. So the point is, we finish in 1 minute instead of 2 now, because of the concept of futures. Now, so these future and value functions are core building blocks for parallelization. You can build up much richer things. And you're not going to use these, most of you. You're going to use these higher level APIs that make use of this internally. So if you use lapply and you have a long list of vectors and you're calling this very slow function, if you do this in regular R, essentially, I mean, we all do regular R here, but sequentially lapply, every item in this XS vector will take 1 minute maybe. Okay, and then there are versions of those one-to-one mappings that you just do future underscore lapply. You can just update your code to do that. And what happens internally is that there will be a lot of boxes created automatically. And they will be sent off to parallel workers, and the lids would be looked at and stuff like this. But it's all done under the hood. So your user interface is typically this. And if you like the tidyverse world, you have map and future map. So it's very easy to upgrade to parallelization. What I haven't said is you can parallelize in many different ways. So the most common one on your laptop or your desktop, plan multisession. That's one setting you do when you start R. The R now alternative to this, there are pros and cons. You can use the call-R package to parallelize on your local computer. And you can use the Mirai package to parallelize on your local computer by just setting this thing. If you have access to multiple computers in your office or at the university, as long as you have SSH access and R is running there, can run there, you can do this one line and it will SSH into these 3 computers, spin up workers, and you can harness that compute power. And if you're lucky enough to have access to high-performance compute clusters, you can use Slurm schedulers to send these boxes out. Okay? So that's completely separated. It's like you program your code, and then where it's processing is a setting. Okay, so let's go back in time. 10 years ago, the first version of Futures, I got the permission to use AI to generate my balloon wall, because I don't have the fundings. And this, so it's 10 years ago, the first release on CRAN. The year after, I'd used R 2016. This was my first use R. I presented this. And the key thing is Future is a very small, lightweight package, works on all platforms, works the same, easy to install. And it's consistent everywhere. So like you create the futures and you send them out and you will get the same results. So that's key in science. Random number generation, everything is like secure. So you don't have to worry about that. At that time, I also showed how you could do HPC. And that was a package called batch job. They replaced that with batch tools later. So I'm just writing a thin wrapper on top of something that already exists. Then at the end of the talk, I gave this. I'd love to see sometimes in the future, pun intended, private to computer-based peer-to-peer compute clusters. And if we now go back to the room, we can do that. Ka-ching. So if you open your computers now and follow the instructions, you could all join a shared compute cluster and work together. Or you have people outside anywhere in the world. So all you have to do, if this is set up, this cluster. So this is saying plan. I want to use the peer-to-peer cluster called Alice Friends. So that means Alice is hosting it, and they decided to call it Friends. And then anything Future apply just works. So how to get started? It's useful to know how this works under the hood. So this is just, I made this as a, what do you say, conference, what is it? Conference development. Constant driven development. First time ever. It's like, I'm going to write the abstract before I implemented it. Because it was like, I've made so many changes, so this should be easy. So there are two components. There's a message board. And the message board is where you announce, I have futures I want to process. So you're not taking the futures and put them on the message board. You put a small post-it note. Oh, I guess I can use this one, like this. And say, I have a future I want to process. And if Bob said, I have two futures I want to process, you put that on the message board. It's very lightweight, so very little traffic. It is centralized now. I don't know enough. I hope someone can make it decentralized. But so there is one small server running. The big thing is the peer-to-peer file transfer protocols, because that grew out of BitTorrents and things like that. So they have very well-established libraries for this. So that comes when a worker later say, I'm going to take this and offer to do work on this. Then on this note, there is a phone number saying, you're reaching out, and there's no more communication on this. You're just reaching out to the owner of the future saying, I'm going to take that. And the peer-to-peer file transfer just magically finds if you're in the same room, punch through firewalls, and send this over anywhere in the world. It's really cool. And to join, you need an account. And this is, again, prototype. There's a really cool service called pico.sh. It's all terminal-based and SSH. You need to have a public-private SSH keys. Most of you have it. If you don't know, you just call that SSH keygen, and it generates it. That means you don't have to enter a password every time you do an SSH. Then you go and SSH into pico.sh. And you get presented with this interface, TUI, not a GUI, and saying, hey, welcome, create a username. So here's Carol signing up, press enter, you're done. No emails, no verification. The verification is from your key. That's it. Now you have a username in the peer-to-peer cluster. So now Alice, somewhere in the world, in R, can now set up this cluster and invite users, Bob and Carol, to have access to it. Basically, this is just like I'm hosting a message board. There's no traffic really going through Alice's computer, okay? And then now we say Bob is doing this. I'm going to run, I have that code and generate 2 futures. What will happen? So nothing will happen because there are no workers. So we need to contribute our resources. So this shows how you can do it from within R. Alice and Bob and Carol contribute 1 worker. And now, all of a sudden, things start working because our workers start taking these. Okay, and boxes are being sent around. This can be done from the terminal. I like this because you don't really have an interactive thing in R. So Alice can launch a cluster like this. And it's easy to launch workers from the terminal. So here's like an example where Alice contributes 2 workers, 2 CP cores, Bob 1 and Carol 3. So that's how you end up with a cluster with 3 workers. Okay. Pros and cons. High latency. Extra high latency now in the first version. The evaluation of 1 + 2 is like instant, but in order to send these boxes, they have to find a way through internet. So that can take 2 to 10 seconds. It's not optimized at all. There's no memory. So I can see if a client and worker already established, it can probably go instantly. But now they retry every time. You can have high throughput because any number of people can join, a number of users. You can imagine a public peer-to-peer cluster. I'm not enabling that because of next slide. But you can have like access to thousands of users or workers. But what happens if Bob decides to do this? So we already have this in R. We trust cram packages and not to do this. But this is like even more. So there's a lot of trust. And how do we protect against that? You end-to-end encryption, so you know you're talking to the right people. You can also run workers in sandbox environments, Linux containers. Some people saying that's not enough. You can break out of a container. So a virtual machine might be safer. I have some prototypes in the parallel package, how to spin those up. But this is not available now. So when you do this now, it runs in your computer as you. But I encourage you to think about this. It's very important. And if you know people or you know things here, please share your knowledge. Future is bright and fabulous. Although it might not look like that all the time, but it is. So I would say stay tuned for future improvements on the horizon, more customized random number generations. This is for a whole Futureverse. Resource specifications. This is very important with this. So in this post-it notes, you can say, I need 2 gigs of memory and a GPU. And I want to implement this regardless of peer-to-peer network or how you parallelize. So that is something on my 10-year wish list. In the near future, I'm going to give you a teaser. If you think FUR and Future Apply are awesome, just wait. In the next couple of months, it's going to be beautiful. And thank you so much, and may the future be with you.